All right, this is for Project 2, Cepheid variables. Just to let you know, there are actually two types of Cepheid variables. This is sometimes called the classic Cepheid variable, or sometimes type 1. Anyhow, I'm going to do an example. This is not the same numbers that you have for your project 2, but it's very, very similar. So with this one, we're using a period of 34 days. I think you'll see why that is in just a second. So what we have to do is look at the graph. All right, so I'm going to switch to that right now. Let's see, where is that? That is right here. All right, so I've switched to the graph. So see, when you look at this, 34 days would be right around here. And so so again, this is the classic Cepheid variables, which have a relationship between the period and the absolute luminosity. That's the important part. All right, so hold on, let me make sure this is recording. Okay, yeah, so it is. So 34 days, we look at this, the horizontal axis, and so you have to draw a straight line up to the curve, the relationship. So we go straight up. I didn't go exactly straight up, but you go straight up, and see that this is why I picked 34 days. If I go, so this is onto the curve for the, it's just a straight line, and then I go horizontally over, and see that's why I picked 34 days, is because the luminosity is 10,000. So it's 10,000 times the sun's luminosity. Okay, so now we can go back to our problem, which I've already indicated all that. All right, so if the period is 34 days, the absolute magnitude is 10,000. All right, so that's the important part of that. Oops, let me make sure everything is still working here. All right, so from the graph, if the period is 34 days, with this type of Cepheid variable, the absolute magnitude is 10,000 times the luminosity of the sun. So that would be 10,000 times the luminosity of our sun is well known to be approximately 4 times 10 to the 26th watts. And so you need one more piece of information to get the distance. Okay, remember what we're trying to do is we're using for project part 2 is we're using Cepheid variables to determine the distance, and this one is this is just an example, but the one that you guys are working on will be the distance to Polaris, the pole star. All right, anyhow, which happens to be a Cepheid variable. All right, so you're given that the apparent magnitude, and often the apparent magnitude is given the symbol lowercase b. So the apparent magnitude turns out to be, and let me say something about this. Okay, so the apparent magnitude is something you would measure in your telescope. All right, in your telescope you would measure the period, right? And of course this is a Cepheid variable, and so you use the graph, and so you've measured the apparent magnitude to be 1.136 times 10 to the minus, that's supposed to be a negative, 10 to the minus 17th watts per square meter. That's supposed to be a 2 right there, per square meter. All right, and so then we use what's called the inverse square law, okay, just like we've done in the past. And so B, the apparent magnitude, is equal to the absolute magnitude divided by 4 pi, also divided by the square of the distance. And of course the 4 pi times the square of the distance comes from the fact that you have a sphere that is increasing in size. All right, so anyhow, we rearrange this equation right here. So that's what we're doing. All right, so we rearrange that equation and then we solve for D. Right, and so D is equal to the absolute, so the D comes over to the other side. You have to take the square root of both sides, so the D is 10,000 times the luminosity of our sun, which is approximately 4 times 10 to the 26 watts, and then you divide by 4 pi, and you divide by one, this apparent magnitude that you measured in your telescope if you were actually doing this. It is 1.136 times 10 to the minus, that's supposed to be a negative sign, 10 to the minus 17th watts per square meter. You're only getting a very small amount of energy in your telescope. All right, so we solve that, and remember the distance will come out in meters. All right, so this distance here, the answer will come out in meters. All right, and we'll convert it to parsecs in just a little bit. All right, so let's complete this problem. So this you just put in your calculator, right? And again, this is just a sample problem. Use the graph that was given to you in the project for Polaris. Anyhow, let's complete this problem. So the distance, when you take the square root of all that, I get let's see, what does it come out to be? 1.67 times 10 to the 23rd meters. 10 to the 23rd, meters. Right, and then of course we're going to use our conversion, that 1 parsec, 1 PC is equal to approximately 3.1 times 10 to the 16th meters, right? And so there's our conversion, and so the meters cancel, and so once you divide that, you get the distance to this particular Cepheid variable as, and remember that this extends our distance scale enormously, by the way. This turns out to be 5.4 times 10 to the 6th parsecs. And another way to write this, and a very common way to write this, would be 5, that's supposed to be a 5. That doesn't look like a 5, sorry. Let me erase that real quick. All right, this thing doesn't erase very well. Sorry about that. I'll be done in just a second. All right, so it becomes 5.6. All right, it still has, and instead of writing times 10 to the 6, we usually will write mega, capital M, megaparsecs. So this is well outside of our galaxy. This is, a very good distance from our galaxy. Remember, for example, the Andromeda galaxy is about 2.5 megaparsecs away. All right, so if it's times 10 to the third, this is just I'm just talking out loud here. If it's times 10 to the third, then you would replace it with kiloparsecs. And usually kiloparsecs, we use that for objects inside of our galaxy, inside of the Milky Way. All right, so and of course Polaris, just to let you know, is part of our galaxy. It's a star in our galaxy. So it's very, very typical. Values are in kiloparsecs. All right, so let's see. Let's pause this. I just noticed I may have made a mistake here. I didn't really make it's really 5.4, not 5.6. This is because I was looking at and so here, let me erase this real quick. So sorry about that. All right, so There we go. So it's 5.4 megaparsecs, right? So 5.4. So sorry, I just sometimes when I look at, when I'm writing this stuff, I see a number and I write it. So it's 5.4 megaparsecs. All right. So I guess I could write that one more time. All right. So the distance to this particular Cepheid variable would be 5.4 megaparsecs, or times 10 to the 6 parsecs. It means the same thing. Keep in mind, this is how Hubble, Edwin Hubble, the actual astronomer Edwin Hubble, in the 1920s determined the distance to Andromeda using Cepheid variables, and he was able to figure out the distance to the next large galaxy over from the Milky Way. All right, so that should get you able follow this, watch it a few times if you have to. It's not really that complicated. So remember, what you're going to do is you're going to look at that graph and look at the period for here. So let me. Of course, this is the graph. Now, the period for my example was way out here. The period, look at what the period is for, without giving it away too much. Look at the period for Polaris and figure out what the absolute luminosity is for that particular star. And again, you'll find it's within our galaxy. All right, so that is it.